We're going to get back to this document. It's a cool Geological Survey of Canada document, but I don't want to discuss that yet. I'd like to discuss first um, the Mississippian in a more general way. And you'll remember, but just so we have a better map of it, you'll remember that we have a shoreline, or at least a kind of a shelf slope break line in Alberta at the time of the Mississippian, where the, oh, pardon me, let's make the shoreline blue, where we have some type of deepening in the area of the Peace River embayment. And then the break to deeper water follows kind of close to where the Cordillera is. And Michelle mentioned the Prophet Trough later on. It's still a low in the Permian, Pennsylvania. And it's here. I know you have this in your notes, so we might as well do it better while we can. So the Prophet Trough. I'm a little shaky today. I'm not sure why. And of course, this is called the Peace River embayment. And it's the collapsed Peace River arch. And if you were to look at the nature of the collapse of the Peace River arch into the Peace River embayment, it's really owing to a set of normal faults developing. And they may have been there already, but these faults are at least activated during the Mississippian. And what was once an island or a topographical high becomes a big, deeper water embayment. And there's faults, and you might remember from EAS 100 or 201 that we show that normal faults are these lines with straight ticks on them, like I've drawn there. And really the whole structure of the Peace River embayment are sets of perpendicular faults that are causing the crust to sink, or even allowing the crust to sink under the weight of sedimentation. And as such, we actually get much thicker strata of Mississippian in the area of the Peace River embayment. So were you to have an oil well that you drilled up in the area of Grand Prairie, Alberta, you would find that the Mississippian is almost a kilometer thicker in some areas there than it is for the most part in other places. And you'll remember that we mentioned that this is all shallow carbonate shell. And different people use different terms. I think for the purposes of this class, whether or not it's a shelf or an atoll or a slope, or, we use ramps, we have all this terminology that's a little more specific about what a carbonate sedimentary environment is. I think it's a little too particular for what we're trying to establish with these slides, which is a general idea of the paleogeography. And you could very much imagine this as being a shallow water tropical setting, but shallow water is a funny term, right? I mean, it normally means something like less than 40, 50 meters deep, but it's not defined in any technical sense. So when I say shallow water, I mean not hundreds of meters deep, but tens of meters up to maybe 100 meters deep. And because we have these carbonate shelves, most Mississippian strata is limestone, or it's been changed later on to dolomite. And I've used the terms dolomite and limestone, dolostone interchangeably, and to me they are. Dolostone versus dolomite. And it's an interesting historical fact that dolomite is actually the name of the mineral. So I'm quite happy to call rock that's made of dolomite the mineral dolostone, like limestone is a limey rock. The stone tells you it's a rock. But dolomite, the rock, has a history of being named for the Dolomite Mountains in Italy. And as such, strictly speaking, the rock type dolomite really is dolomite. Dolostone is not the correct term. I just like it because it's a bit more self-evident. So this is really what our world looked like. And you remember I think I said last lecture that I rather cavalierly said the equator did something like that. And then I double checked, and that's not the case. It's really very similar to the Devonian, but it is moving throughout the end of the Devonian and into Mississippian times, such that by the time you're in the Mississippian, you are pretty well, whoops, no. I hope I can undo that. Let's see. There's got to be an undo button here. Or not just redraw, right? So the equator is doing something a bit more like this, with north being that direction. And so we're still in a nice tropical climate during the Mississippian. And this is moving throughout Mississippian time. And you'll see it in different diagrams or different maps, paleogeographic maps, as kind of in random, or not random, but variable orientations. And that's because we don't know exactly what paleo north direction was. It's interpreted from data sets like magnetostratigraphy. It's the inherent magnetic signature in rocks that let us know their relative position to north when they were being laid down, and that has to pass through time. So there's still some error in our measurements there, even though we can do a fine job of it these days. So I'd say all in all, this would have been a nice country to live in, probably good fishing, warm seas, good storms. And I'm thinking I'm going to get back to this map. We discussed it briefly on Friday, but let's just go first to the cross section of the Mississippian. And I'm going to greatly simplify the stratigraphy here. And we're going to start by going back to the uppermost part of the Devonian, and let's see who can type quickest here. What was the uppermost formation that we used in our simplified stratigraphy of the Devonian? Does anyone remember? Or you can say it out loud if that's easier. Palliser, thanks, Margaret. Yeah, that's good. Oh, and Palliser, yeah, that's good. Thanks, Nick. Yeah, Palliser, good for you guys. I like it when people listen and learn. So let's start down there. We're going to start in the Devonian. And we're going to start with the Palliser formation. And you probably remember that it's a nice limestone. And below, or I should say above the Palliser, is an unconformity. There's time missing. And at that time, you know, most of these unconformities, although I don't think you can quite say all of them, but most of them really represent times when either sea level was dropped or tectonic uplift of the continent lifted it above sea level, because unconformities, for the most part, do represent missing time that's owing to erosion. And the easiest way to erode stratigraphy is to expose it to conditions above sea level, so to erosion and weathering and whatnot. So it's worth remembering that quite often these unconformities, and I would say you'd normally say these unconformities represent subaerial exposure. And it's just, I think, really healthy from a geoscience point of view to kind of link these processes to an outcome. And so the surface is the outcome of the uplift or down or falling of sea level, such that that stratigraphy gets eroded by subaerial processes. On top of this, though, we have a bit of a flood, and ocean level comes back up. And in western Alberta, the Exshaw Formation is deposited. And you'll remember we briefly talked about the Exshaw on Friday when we were talking about its importance as a source rock for Alberta. So as a source rock, the implication there is that this gets buried, it becomes thermally mature in some way. And in that thermal maturation, it starts to expulse oil or perhaps gas, and those gases move on, usually migrating through buoyancy forces up dip, up geology, until it's caught in a reservoir. So this is the source rock part of things. And it's a very important source rock in Alberta. It might be volumetrically the most important source rock, but I mean, that's of course susceptible or open to debate. So the green dot just means it's oily. It's gassy too, so we can put a red dot there as well, but let's focus on it as a source rock. And so the marine rocks, this is a marine environment, this one. And so it was subaerially exposed here, but now this is a marine shale. And you might ask how we know it's a marine shale, and normally we would do that merely owing to the fossil content, although most good shale rocks, most regionally mappable shale rocks are decidedly marine anyway, but the fossil content of the Exshaw Formation confirms this. So this is more in the Alberta side of things. And if you took off over here to the Williston Basin, Saskatchewan side of things, this has an equivalent that we would call the Bakken Formation, which in the Williston Basin is the most important source rock over there. So there's something that regionally has happened in the Mississippian, that this shale has been deposited all around North America. And in the Bakken, in its Bakken expression, it's a very oil-prone source rock. That's basically was the backbone of America's oil recovery, oil production recovery in the early 2000s, all the way till the present, really. They're using more and more advanced techniques like fracking and drilling deeper and deeper Bakken Formation wells. But it's been a very important play. In Alberta, the Exshaw has been much more important as a source rock than it has as an unconventional oil reservoir. So it's important from that point of view. On top of the Bakken, we're just going to put the Banff Formation here. And we'll stick now with the Alberta side of things. I don't know the stratigraphy of the Mississippian Williston Basin very well at all. The Banff Formation. And the Banff Formation, it starts to develop. Down at the bottom, it's more shaly. But with some calcareous beds. And as you get up in the Banff Formation towards the top, it really is a good old limestone. And it's exceedingly fossiliferous, so its biostratigraphic age is pretty well understood. It has fossils, including corals in great abundance, crinoids in great abundance, lots of brachiopods, and all of these features allow us to tie a stratigraphic age to it. because the Banff Formation is a bit on the shaly side, it's not normally a target for resources like hydrocarbon resources. But if you go to the mountains, you almost invariably find the best fossils in the Devonian Mississippian package in the Banff Formation. And if you take a geological map along with you, and you can sometimes find where trails cross the Banff Formation in the more limestone part, you'll find great beds of that are just, the rock is made of invertebrate animal fossils and skeletons. So a really nice rock to collect when you're not in a national park, and a really nice rock to view when you are. Let me just get this. Share that with you in a few minutes. So above the Banff Formation starts the Rundle Group. We'll do this a little differently because the Rundle Group is a pretty large-scale group of strata. That you can view in Jasper, Waterton, just outside of Waterton, Banff, and whatnot. And it's composed of 4 main formations, and it's normally viewed as the Pekisko, then the Shunda Formation, then the Turner Valley Formation. You know what that's named for, the Turner Valley. Turner Valley Formation that happens to be an outstanding reservoir in the area of Turner Valley as well, and provided a very large oil field for Western Canada. And then on top of this, the Mount Head Formation. And all of these are variably limestones, and some of them are dolomitized. The Turner Valley, for example, is commonly dolomitized, and so its porosity and permeability can be pretty impressive, whereas the Mount Head tends to be very microcrystalline dolomite and doesn't normally make good reservoirs, so it's pretty variable. If you go into other parts, like northern part of Alberta, the Shunda is more or less equivalent to the DeBolt Formation. And the DeBolt Formation I mentioned because it becomes an important resource rock up in the area of DeBolt, interestingly enough, in northwestern Alberta. And the area of DeBolt is east of Grand Prairie by about 50 kilometers, maybe a little bit more. And so all of these Mississippian formations, but the Turner Valley and the DeBolt are really the ones that normally have the oil or gas potential. So you can just make a note of these. And to varying degrees, explorationists actually still explore for Turner Valley and DeBolt Place because they can be difficult to find in the subsurface, which means that's actually good news, believe it or not, because it means maybe they're not all discovered yet. Oh, that's hard to say. On top of all of this, small time gap, a smaller unconformity, we stay in the Mississippian, and you go into what is the Etherington Formation. But really, the Etherington Formation can be difficult to tell from the top of the Rundle Group too. So the Etherington Formation, and it's a limestone that I mean, it's important because that's really the formation that collapsed at Turtle Mountain and was a big part of the Frank Slide. So it's a big mass of dolomitic limestone or dolomite that was being that was folded over at the top of Turtle Mountain and failed a little more than 100 years ago now, I think. So that's the Mississippian strata in a nutshell. And let me just get a sip of my coffee. And I'm going to just take a couple minutes because we couldn't write down all of these formations last time. And by the way, in Michelle's note, she tells you the order of things, and I would expect you to make your own little stratigraphic cross section from Michelle's work here. Now, remember from Michelle's slide presentations, I'm so sorry for mumbling. Now, one thing I want to say here is, remember, I've shown this strata as planiform or pancakey, but it's not, right? This strata is dipping up the limb of the Western Canadian Sedimentary Basin, and it encounters an unconformity that is below the Permian. There's an unconformity below the Permian, a pretty good one actually. Subaerial exposure. There's karst at the top of the Mississippian package, and that karst is pretty well developed in areas like Jasper and parts of Banff. So this is an unconformity here, and I'm just going to show you something kind of neat there, that there's an edge then to the Mississippian strata, and that edge is called, by the way, a subcrop edge. And that subcrop edge really is telling you something from the map point of view. Like, let me explain this map to you. You'll have it in your notes, so you can figure it out on your own as well. But this shows some of the formations I was talking about: Banff, Pekisko, Shunda, Livingston, Turner Valley, the Bolt Prophet, so on. And what we're really interested in are the Shunda, Pekisko, Banff, Exshaw units. And you can see there's a zero edge indicated here. And that zero edge is the subcrop edge, okay? So if you go to the map of Alberta, you can see, okay, this is that green line right beside Edmonton there. That's the edge of the Exshaw, Bakken. But in this area, Exshaw, it's the approximate edge. Okay, so here's the question. Based on that map, is there any Mississippian underneath of Edmonton? Is there any Bakken formation if we drill directly from Edmonton? What are the opinions here? No opinions. There isn't any. That's right, Nick. No, yeah, good, Dawson. Thanks, Margaret. No, there's none. Okay, if we drilled here, we would actually we would go encounter, we go straight from Permian rocks, more or less, into Devonian rocks, right? So that's something you need to remember, is the formation of the Western Canadian Sedimentary Basin limb with these several angular unconformities plays a big role in what that stratal distribution is as you go from Western Alberta to Eastern Alberta. For example, if you went to Fort McMurray, you're standing there. If you drill an oil well in Fort McMurray, although well, let's just leave that for what it's worth, you go straight from Cretaceous to Devonian. Everything else in between is gone because McMurray is way over here at the edge of the basin. So everything that's underneath McMurray is all Devonian. It's kind of interesting. So that's the significance of the angular unconformities that are in the Western Canadian Sedimentary Basin. They limit the distributions of these strata. So an explorationist isn't going to look for Mississippian strata east of Edmonton, for example. And this map's quite nice because it shows you something conceptually that's really important. You have the base of the Mississippian here. That's the base of the Mississippian. And you have the top of the Mississippian over here. So this is older, younger, younger, and youngest, okay? And that's because all of these rocks are dipping. Okay, let me just change color there. All of these rocks are dipping in this direction, meaning that as you go from east to west, the strata become younger. You can imagine that. I've drawn a very misleading diagram here. It has its purpose, but just so as not to be confusing, we can show that relationship from some of our other diagrams. We have an unconformity. We have strata that share an angular discontinuity with that. And through Steno's law of superposition, we know that this is the oldest rock, this is the youngest rock, and younging is in that direction, meaning that if the map view, we see exactly the same pattern. We see oldest rocks in the map going to youngest rocks in the map. Kind of an important concept. Anyone have questions about that? Okay, fantastic. We already talked about the resources and this real cross-section from the Turner Valley play from a 1953 publication from the CSPG that I put on your e-class folder for you. On the final exam, I'll remind you that I want you to review this article. That's what's in the Calgary Herald, some rock types, a history. I glossed over this map before because I was getting rattled without my stylus, but here again, we can see, and I just want to emphasize that we can see the oil and gas reservoirs. They're in the traditional green for oil, red for gas, and I wanted to point out that, again, that the up dip bits of these are gas charged, and that's because gas floats on oil and oil floats on water. So this shows a nice distribution of maps. Most of this stuff down in the south is Turner Valley Formation. There's probably quite a few exceptions. By the time you get up here, there's where the Peace River arches. You can see the perturbations in the structural top of the Mississippian, and you can also see there this distribution of small gas fields that are all associated with the DeBolt Formation. Some rock types. I never labeled any of these last time, but here now you can certainly see the crinoids, right? No one's going to argue about that. So that's a crinoid. We've got it. There we go. And these are the ossicles that I was talking about last day. I couldn't draw them because these are like discs. And the discs, you could think of as being like hockey pucks. and they stack up on each other. Going through the middle of these is a notochord that keeps them all together. And then at the top of the structure is what's called a calyx, and it's got a big kind of tentacled looking structure, but the tentacles aren't really tentacles. They're made of aragonite or calcite as well, and they're segmented little palps that are used for things like picking up food, even dragging the crinoid along. Even though it has a plant-like appearance, some of them could move. And it's an echinoderm, so it's related to starfish and irregular echinoids and stuff like that. Most of what we see in this rock here is crinoid. And then back to this rock here where these are the bryozoans here. And you can see more crinoids like that. And then, of course, that's an example of a brachiopod. So I didn't explain this very well last day. I probably should have just given you the day off. We didn't. Turtle Mountain, this is where that fold is. And if you go to Turtle Mountain, you can climb up here, as I mentioned, and then there's the fold up in here. And this part of the limb of the fold collapsed and was the instigation of Frank Slide. A disaster indeed. But that is a hike that's worth doing. I mentioned it already. Mount Rundle, I wanted to go back to this just because now we can put it in the context of the stratigraphy or the Banff Formation. Is down near the bottom. Town site of Banff is over here. And this is Rundle Group strata up here. And this is a very friendly mountain hike, one well worth doing because it's not a technical challenge. It's what we call good exercise in a scramble. So that's and you're rewarded with a heck of a view after. Mount Rundle, this is a view from Mount Rundle. We went over that. Crow's Nest Lake. I wanted Crow's Nest Lake. So Crow's Nest Lake, remember the Exshaw is here, right where the recessive part, there's a notch there, and that's because the Exshaw is a shale, so it weathers very easily. So you get these notches in the mountains. Quite often you can see these shales go right up the mountain as a recessive ridge or an eroded ravine, so to speak. You can see it good from the roadside here, right? You can see how recessive the Exshaw is. For simplicity, we'll call this all Exshaw. So on top of this must be the Banff Formation. It has a characteristic look of the Banff where it's a little shaly and limestoney at the bottom, and then as you go up, it tends to turn into more of a limestone. And then below this is that Devonian unit, the Palliser. The Palliser is, it's interesting because it's present throughout the Front Ranges and main ranges, but more the Front Ranges of the Cordillera, and it's not very fossiliferous, and that's because the Palliser contains an extinction event in it. That's the Franian-Famennian boundary. These are stages of time, so they're subsets of the periods like the Devonian period. And you don't need to remember them really, but the Franian-Famennian boundary is in the Palliser. And that's one of the big extinctions of all times. It's probably the third biggest extinction event, arguably the second. And that was an extinction event that really uh, devastated marine life. And there's a great big reduction in diversity of animals at the time, and it's all sea life and vertebrate animals. And what caused the event? Yeah, so Dawson, that's a pretty good question. That's been a subject of debate for a very long time. Uh, some time ago, people started trying to associate meteorite impacts with the Franian-Fumenian extinction event, which is in the uppermost Devonian. And there's not a lot of direct evidence for that. And last time I looked it up, I don't think there was any evidence of a crater that's strongly dated to that time, although I might be wrong. But, you know, there are other things that can contribute to the extinction event, you know, like, for example, if ocean circulation becomes compromised because of the position of the continents, as might have happened in the Permian, end of the Permian later on, you know, there's different possibilities. But yeah, I haven't looked up the Franian-Fumenian extinction for a long time. About the extinction PBS eons, I wouldn't be surprised. Let me have a look. I'm sure they've got new ideas that I haven't looked into for the Franian-Fumenian boundary. So I'll just take a note to get some new information for you. Haven't thought about it much for a while. And I'll definitely check PBS eons. But you know, us paleontologists and geologists will, when they're trying to solve an extinction event, they tend to throw everything at it, uh, including the kitchen sink, and you can usually find an interpretation that suits everybody. Like let's just say it's hard to sometimes know what caused an extinction event. We've been here. I should just write this down. PBS eons. It'd be fair to say that a lot of these events we argue about for years and years, like the Permian Triassic extinction, which you'll study next briefly, albeit, is one where there's a lot of things point towards, like there's a change in world oceanic circulation, there's a great amounts of volcanism in Pangaea, up in the area of the Siberian Craton, and there's oceanic um, geochemical assessments that show that ocean chemistry got goofy, and we've literally argued about the cause of the Permian Triassic extinction for a century now. And everything that you could still publish on the Permian Triassic extinction is still an interpretation, and people will argue about it. So, yeah. Anyway, let's move on from there. I'll look a little more into the Franian-Fumenian just because it's a really good question that I couldn't answer very well. And there's Moose Mountain. There's actually a picture of Moose Mountain here. Now we can see the Banff, Pekisko, Shunda, Turner Valley set. So the lower three formations of the Rundle group are right there. And if you were to refashion this diagram, you would also add that this was Rundle group. So again, Moose Mountain it's a bit more remote, and I don't think you necessarily have cell phone coverage if you're up there. It's not like the mountain parks, but not a bad hike up to the top of Moose Mountain if you go from the easy side up, which is what anyone with common sense would do. And now I just want to look at a couple things here. I'm going to put this into the lecture notes when I include them. It's from your first year textbook, EAS 100, the Blue Planet. No, this one's from the other one. I can't remember the name of it, but it's from your textbook. I used to teach the course. And so this just shows a paleogeography map of the Mississippian. It's suggesting that there's some highlands in Western North America associated with this orogeny called the Antler orogeny. That's a Devonian Mississippian event. They show it as expressed in Alberta too. That's what these are here. As far as I know, there's not really any great evidence of Mississippian exposure in Western Alberta, so I feel like the map's a little bit flawed. Where the red circle is where Alberta is. That's the Western Canadian Sedimentary Basin, and you can see the Williston Basin rather conservatively indicated here. It's really probably a little bit bigger than that, but those are the basins that we're interested in Western Canada. And you can see there are highlands that are related to the North and the Franklin Highlands, and in kind of associated with an incipient or early building Appalachia on the east. And you can see the position of the equator there, where Alberta is arguably, in this case, well north of the equator. But I've found several sources that are in conflict with this. Let's just say it's not that far from the equator, though. And then I wanted to show you some resources you can get to. This is a geological survey memoir, available as a digital memoir. I downloaded this because it has a lot of the Rundle stratigraphy in it, and it's the geological survey calls these compilations of work memoirs. So quite often, if you look something up in geology and it's done by a geological survey, it's called a memoir. And so don't let the name fool you. It's a compilation of work over a few years that's usually includes some maps and sections and fossil analyses and stuff like that. And we've made these geological memoirs in Canada for much more than 100 years now, back to the late 1800s, I think. And Canada was a very early adopter of the geological survey, so we've got a really strong tradition of geological surveys. The author of this this memoir is P.S. Warren, Percival Sidney Warren. He was a U of A geologist and head of the geology department in the 1920s and 30s, a very famous geologist in his own right, and he did this work in partnership with the Geological Survey of Canada, and this goes back to 1927. And the reason I bring this all up is because you can actually go to the Geological Survey of Canada, and I'll just show you where to do this. Just take a note, because this is such a resource. I just can't, I think I can go right there. Good. Yeah, it's called GeoScan. So you can search GeoScan. So if you want to search GeoScan, so this is the government of Canada. It's called GeoScan, and you can do things like if you wanted to search the geology of Edmonton, you can do a search of the geology of Edmonton, and some things come up. And sometimes you get a whole lot of things: combined tree ring data, preliminary analysis of groundwater. So there, okay. So if I don't like what I see, then I'll refine the search terms a little bit. And there's an stratigraphic framework of the Alberta Basin, Edmonton, Alberta. Let's look at this. And then you go downloads. Woohoo. And then you can get it as a JPEG or a PDF. Unfortunately, and it's a little hard to believe, these are not geo-referenced, and it'd be so great if they were geo-referenced, but I'm just going to open up the map. Oh, it says it's damaged. Maybe it's still downloading. I'll try the PDF. Oh, yeah, I'll just open it in here now. This is a black and white map, so it's not as remarkable as you might see here. It looks like it's a topographic map. I never did the bother of actually seeing what's going on with this map before we opened it. So there you go. But it's a great resource because you can usually find things like this very old report. And I'm going to go back to the report here now. And then if we go to the report, you'll see what a great resource these government publications are. So Percival Sidney Warren, 1927. It's a long time ago, I guess, but you know, the work they did. This is interesting. Eh? He was doing this work in the area of Banff and east of Banff. And there's Rundle Mountain, the profile of Rundle Mountain. And he talks about and describes the Rundle group in pretty good detail in this memoir. And then he includes things like a geological map. It's not colored, but you get the newer ones, and some of the newer ones are colored, but it doesn't really matter. You can see it has all the elements that we expect of for a geological map. It's got some type of legend here. And that legend is showing the distribution of Cambrian, Devonian, Mississippian, Carboniferous, Triassic, and Cretaceous rocks. You can see that their outcropping profile is pretty clear here where the ridges are. And there's the town site of Banff right in the middle of the screen. And so you can look at the stratigraphy that way. And I'm just saying this, oh, there's a cross section on the left, shown sideways. And shows some of the main formations that have been around for a long time. So we still use the name Spray River group for the Triassic, and obviously the Rundle group goes all the way back to before the 1920s too. And then at the end of it, Professor Warren was actually as much a paleontologist as he was sedimentary geologist and stratigrapher. So I would call him a paleontologist and biostratigrapher, someone who looked at the world through the lens of its evolving life and classified these stratigraphy and their age on the basis of their fossil content. And that's really what the art of biostratigraphy is. And I'm just moving on to the end here where we can get, now there's some compositional data here, but we're not going to worry about that. We're just going to go to the fossil pictures. Building stones. Yeah, they were doing a part of the study that Warren did was to actually assess some of the economic aspects of the Bow Valley area there, and that was before Banff was national park. So it might have been a prelude to resource assessment before it became a park, actually. And then these are showing some of the fossils that they find in the Rundle group and describe in great detail. And they use these to say, well, this rock's older than this rock. And they base it on this idea of the law of fossil succession that we talked about in lecture number 2, that fossils occur in a certain order throughout the global sphere. And anyway, it's now 3:24, so I took you about 10 minutes longer than I intended to today, and you have asynchronous materials. I'll be ready for you Wednesday, and I'm sure you'll be ready for me. So are there any questions? Let me say, I wanted to get the exams done for today or Wednesday, but with the way I was struggling getting all my lecture materials together for Wednesday, so I really don't think I'll have the final grade assessments to you until Friday, but I won't be later than Friday because Professor Johnson is lecturing Friday, so I don't have to work feverishly on thinking about what to present to you on Thursday and Friday. I'll have some time to get my notes together. All right, well, seeing no questions, I'll leave you off to your asynchronous business. So Friday will be asynchronous. Stephen, you're actually giving that lecture live, aren't you? Oh, Stephen checked out. He had a meeting to go to. I think Stephen's actually giving the lecture live and then taping it.